Good afternoon everyone, and welcome to today's worked exam answer video. At the request of one of you lovely followers, I am having a look at a couple more rate equations questions whereby we need to work out the orders of reaction, or perhaps like in the second question, use the orders of reaction to figure out, in this case, one of the initial concentrations of the reactants. And there's actually two ways we can do the second part of this question, and I'll of course show you both ways. So initially we've got a table of data. It says the question involves the use of kinetic data to deduce the order of a reaction and calculate a value for the rate constant. I chopped that part out. The data in table 1 were obtained in a series of experiments on the rate of reaction between compounds A and B at a constant temperature. Now, when we get a table like this, there has to be two experiments whereby only one of the concentrations has been changed. And that applies whether there's two reactants or three. It might be that there's three reactants and it looks like two of them are changing, but one of them is in fact zero order, so has no effect on the rate. So here, the concentration of B stays the same between experiment 1 and 2. And therefore, the first two experiments we need to compare are experiments 1 and 2, because all of the change that we see in the rate has to be caused by the change in the concentration of A. So between experiment 1 and 3, we multiplied the concentration of A by 3. And if we then work out how the rate has changed, I get that to be 9 times bigger. So if the concentration of A has been multiplied by 3 and the rate is times by 9, because 9 is 3 squared, A is therefore a second order reactant. We now need to do the same for B, but you'll notice that there aren't two experiments where only B is changing, and we're therefore going to have to use what we've just figured out about A and have a think about how changing A would affect the rate, and then see if there's any further change in the rate that can be explained by the change in concentration of B. Now, just because they're next to each other, I'm going to choose to compare experiments 2 and 3, but I could also choose 1 and 3 as well. We have to use 3 because that's the only one where the concentration of B is any different from the other two. The other reason why using experiment 2 might be easier is because the change in the concentration of A is a little bit easier, so yeah, but either would work. So yes, we can see that the concentration of B between experiment 2 and 3 has been halved. We've divided by 2. We also have to take into account the fact that between experiment 2 and 3, the concentration of A has been doubled. And because A is a second order reactant, that means that that would cause the rate to then multiply by 4. Or 2 squared, and I'm going to work out what that is, and I have named that the intermediate rate. Now all I mean by that is this would be the rate of reaction if only the concentration of A was changed, or they were both changed but only A had an effect on the rate. So by doubling the concentration of A, the rate would increase to 7.56 times 10 to the minus 3. Now that's not the final rate for our experiment. So I can now work out what happens to decrease the rate from 7.56 times 10 to the minus 3 to 3.78 times 10 to the minus 3, and that is dividing by 2. And because the concentration of B was divided by 2, and we can see that the rate was affected the same way, dividing by 2, that therefore tells us that B is a first order reactant. And then from there we can answer the question by deducing the rate expression. So the rate is going to be equal to K, the rate constant, and then concentration of A squared, because that one's second order, and then the concentration of B. So that's the first question that I want to talk you through today. And the second is this one here, whereby we're doing something slightly different because we've been given the rate equation, so we know the orders of P and Q in this particular question. we're trying to then work out what must have happened to the concentration of Q between experiments 1 and 2, and thus what the initial concentration of Q was. So as I said, there's two ways of doing this. The first thing that I would always do if you've got a rate equation provided and a table of data just helps me to put the orders into the column headers, just for reference. Now the first way that we can do this is really similar to what we've just done. So we can see how the concentration of P changes between experiments 1 and 2, and it's got 3 times bigger. And because P is a first order reactant, we can then say, okay, if only P was changed, or only changing P had an effect on the rate, what would that then look like? So we do 0.4 times 3 to get 1.2. Now here it's a little bit different because A, we know that Q is going to have an effect because it's second order. And yeah, I guess that is the main difference here. We know that this is not going to be 0.5. Or we know that the intermediate rate that we came out with is not going to be 0.8. So again, we can then figure out how has the rate then got to change as Q changes. So the rate's got to decrease from 1.20 to 0.8. And to do that, we are dividing by 1.5. Now, because Q is a second order reactant, as we saw in the first question, for a second order reactant, whatever we did to the concentration, we did to the rate squared. So this 1.5 is whatever we've done to the concentration of Q squared. So if we're going from concentration to rate and squaring, if we're coming back, we're going to have to square root. So to go from 0.5 to whatever the concentration is here, we are going to have to divide by the square root of 1.5. And that's where people start to not like this question, but that gives us a concentration of 0.408, which is thus option C. It's easier to do when you're trying to work out a gap in one of the concentrations for a first order reactant, because whatever happens to the rate, if it was divided by 1.5, then the concentration would also divide by 1.5, and it only looks horrible because 1.5 is not a squared number. Had we have got this as being dividing by 4, people perhaps would have been slightly happier going, oh, well, 4 is the change in concentration squared, so therefore the concentration has changed by dividing by 2. But the same principle applies. Just because this is this squared, we can just square root whatever we get here. Not very nice numbers though. So how could we do that a little bit differently? Now, this question up here, part of it that I chopped off said that we were going to calculate a value for the rate constant. We can do that here as well. So using the data from experiment 1, I can work out a value for K. So first of all, we'd need to rearrange the rate equation. So rate is equal to concentration of P times concentration of Q squared. And then I can sub in the numbers from experiment 1. So the rate is 0.4, and then concentration of P is 0.2 times by the concentration of Q squared. And that gives me a value for K of 8. Now, if you were asked to do this as a question, it would also ask you for the units of K. So we've got mol dm minus 3 for rate, and then we're going to be dividing by 3 lots of concentration units in total. One will cancel with the mol dm minus 3 in the rate, so we then have 2 lots of mol dm minus 3 on the bottom, which will become mols minus 2, dm plus 6. And then we've still got the S minus 1 from the rate units. Now, of course, that's not relevant for this particular question, and you wouldn't need to show any working out here because it is a multiple choice. But once we've got our value for K, we can then rearrange the rate equation to get Q. So start perhaps with the concentration of Q squared being equal to rate divided by K times the concentration of P. And then we can sub those numbers in for experiment 2. So 0.8 for the rate, and then the rate constant is 8, and the concentration of P is 0.6. That then gives me the value for the concentration of Q squared. So then I just need to square root that. Which should get me to the exact same answer, and does. So you might have a preference as to which method you prefer. You might be happy with both of them. My suggestion would be that if you're happy with a method and you've been using it consistently, to stick to it. But what I would also say is that if you are kind of using this method, the table method, and on the day tomorrow you just for the life of you can't make it work, do the alternative. Because even if you have to work out K and you're not getting any marks for doing that, you don't need to show you're working. So long as I know that K is 8, I can then do my rearrangements to get whatever value is missing in the table. You can work out rates that way, you can work out initial concentrations that way. So long as you have one full row of data, you can work out K. So it's whatever you prefer to do for these sorts of questions. Either method is fine. Ultimately, for these questions, you get 1 mark for every gap in the table. So however you do it, as long as you get the right answer, all is well. So I hope that's been useful for some of you. And if there's any other queries that you have ahead of paper 2 tomorrow, please do let me know. My plan is to record some paper 3 videos and release those over the course of the week. Some practical questions and some multiple choice questions. Again, if there's anything specific that you are struggling with and like help with, please just let me know. Final push now, guys. You got this. Just give it everything. Try and take care of yourselves at the same time though. And I wish you all the very best for the week ahead. And I will be back with more videos in a day or 2. Take care of yourselves. Bye for now.